That's just the transport equation. So that's a crucial remark for planar flows in 2D. The vorticity is just transported by the velocity field. The vorticity omega obeys the transport equation. And this will be very, very convenient for the mathematical analysis. Okay? That's why 2D flows, the Euler and the Navier-Stokes equations, they are much better behaved in 2D than in 3D. All right. Okay, but we could say, oh, it's magical, we have no pressure anymore in the equations. We have this nice transport equation, for example, in 2D. Still, you must not forget that here you have omega, but you also have u, right? So, the equation is not closed in omega. There is also u. So if you want to treat everything with omega, you need to recover u from omega. Okay? And it turns out that you can do that. So u can be expressed as a non-local operator applied to omega. And I can show you that in 2D because it's in 2D it's very, very useful. So, example, let me show you how you can express everything in terms of omega in 2D. So in 2D, what do you have? The divergence of u is 0. Right? So, you know, this is, if everything is smooth, which is everywhere, you know, I made some kind of formal calculation, so I assume that everything is smooth, nice. So if divergence of u is 0, you know this is related to Poincaré theorem in differential geometry. You can say that u is the orthogonal gradient of some scalar function psi. Okay, so this is minus d2 psi, d1 psi. Psi is called the stream function. Because the streamlines are the isovalues of psi. Then, if I express u in terms of the stream function, then I can compute omega. Omega, I said, was the curl of u, so that's d1 u2 minus d2 u1. Take this expression, you find the Laplacian of psi. Okay. So again, if everything is nice, I can invert to get psi in terms of omega and then u. So you can take psi to be Laplacian of -1 of omega and then u, which is the orthogonal gradient of psi will be the orthogonal gradient of Laplacian minus 1 of omega. Sorry. What is this? Or maybe I should go barefoot. Will be needed later, so I just write it down. So psi, so we are in 2D here. That's 1 over 2 pi log of x convolution with omega, and then u of x will be u of x will be 1 over 2 pi integral over R2 of the vector x minus y. You turn it, this is the orthogonal of the vector x minus y squared, u of y dy. So this is how you recover, sorry, this is omega here, omega. Okay, this is how you recover u from omega, the velocity from the vorticity, and this is known also in electromagnetic, it's called Johansson law. So that's what I wanted to say about vorticity. So in the last few minutes, a last general remark. PDE. About energy estimate. Okay, so starting next lecture, we will build solutions for these Euler and Navier-Stokes equations, and there is some very simple but crucial thing, which is having an energy estimate, right? So that's multiplying by u the Euler or Navier-Stokes equation. So you can consider both. So we write dtu plus u dot rad u minus plus gradient of E minus mu delta u equals 0. And divergence of u is 0. Okay? And okay. Mu equals 0 will be Euler. Mu positive will be Navier-Stokes. So you can cover both cases, of course. So what is the energy estimate for this PDE? You just multiply by u and integrate. Let's see what happens to each term. What do you get? First term is the integral over Rd of dtu times u. That's just d over dt of the integral over Rd of Euclidean norm of u squared over 2. Remember? That's the first term. to the pressure gradient when I take the scalar product with a divergence-free field. As I said before, it's orthogonal, right? So you should get 0. Another way to see that it's orthogonal, you make the integration by part. So what you get is minus P divergence of u. And divergence of u is 0. Okay, so that's how you see it's orthogonal in L2, right? Integration by part. So this goes away when you multiply by u and integrate. Then, okay, what about the diffusion term? So for Euler, there is no term like this, but for Navier-Stokes, you have a term like this. And when you integrate by part, what you get is the integral of the norm of the matrix gradient of u. U is a vector field, gradient of u is a matrix, right? You take the norm of this matrix, take your norm, you square. Right. And last, let me put it here. What happens to the nonlinear term? This is the integral of u dot grad applied to the scalar function u squared over 2. So when you do the integration by parts, you will get divergence of u times u squared over 2, and divergence of u is 0, so you get 0. So more generally, what you get is so for a divergence-free field for V such that divergence of V is 0 and any function f, what you get is that the integral of u dot grad f times f, that's the same, right? That's the integral